Okay, guys. So let's start. So the next speaker will be Timothy and Timothee. Distributional, yes, that's nice. Very distributional representation, semantics and text. So please start.
Hi, so thank you very much for having me here. I'm Timothee Mickus. This is what we work with Timothée Bernard from Université de Paris. And yeah, today I'm here to talk about distributional semantics and whether semantics is a good use of the term here. So let me start by a fairly simple thing. What do we generally use as a definition for distributional semantics? And very often, especially in NLP, the only definition you get is a quote to verse 57, you shall know a word by the company it keeps. And there's really not a lot of thought that's being put as to what exactly that entails. However, if you do go see the literature in a bit more detail, one thing that is very obviously a point on which to insist is that representation that we derive from distribution are assumed to be semantic. Here are a few examples. This one comes from Lenchi 2018, and here he says he equates distributional semantics to vector-based semantics, and he says that context characterizes the semantic behavior. Other example, that would be Bolida 2020, where she points out that distributional semantics induce semantic representations from context events. And third, because rule of threes, this is one by Pavlik. One by Pavlik, where she states that distributional semantics models define the meaning of word in terms of the context in which they occur. So really the one point that is very constant in these different distribution is that we use context and what we get out of it is meaning. And this is the narrative I'd like to push back on today. I'd like to try to take another route and see what we can get out of it. And to start with, I'll start with a tentative definition, more like a working one rather than something that is completely definitive yet. And the idea is that we are going to call anything that models the probability of a word given its context distributional. And we expect that probability to be based on to be estimated through textual data and so on. As to why that is a pretty reasonable definition to hold, we can point out that this actually already covers a lot of the existing frameworks that we tend to call distributional semantics, both neural but also non-neural and so on, both static embeddings and contextualized embeddings. So it's pretty inclusive in terms of what it's supposed to denote. It's also interesting because it explicitly connects with the structuralist background of distributionalist approaches. The reference to Solgren here is a very interesting sort of quote if you're interested in that. Suffices to say that this is the probability of a word given in context, so it's the same as trying to fill the slots in a sentence, which is essentially a paradigmatic axis in the structuralist sense. Okay, however, one thing that's pretty interesting to discuss here is that it also begs the question, do you actually need semantics to model that probability distribution, right? And this is what we'll be talking about today, and we'll break it down in two sub-questions. The first one is, do we have some evidence that distributional representations do capture something of semantic structure? And the second approach that we'll try to take is whether we have some evidence that the distributional representation we have captures something of semantic features as well. Starting with the first, in practice, what we'll be doing is we'll just be using a RSI style methodology. So we're just going to sample pairs of sentences. And then for every pair of sentences that we have in our sample, what we're going to do is that we are going to compute pairwise distributional similarity. We're going to compute pairwise structural similarity, and then we'll just report the correlation scores between the two. Which opens an interesting question. How do you measure structural similarity? And here, one thing we proposed with Timothée was something we called structural views. And the idea is that we're just going to have a look at a graph representation of a sentence. That graph should be labeled and directed, and we're just going to look at the multi-set of all possible sequences of label that you would get from a random walk of that path. that graph. So the general idea being that for some length up to k, you are going to see what sequences of 3 labels you could see into your graph, and then that would get you a first idea. And obviously, you can take different values of k, so from 1 up to some maximum value k hat, and just compare those to get an idea of what happens when you incorporate both shallow information as well as more chain dependency style representations. Right, and to just compare the two, after that, what we have is that we take a simple intersection over union style of similarity, which gets us a basic idea of how similar the graphs are. What's interesting there is that it's applicable both to syntactic trees and semantic DAGs, so it's pretty convenient in terms of exploring different structures, linguistic structures, and comparing different linguistic structures. It's also pretty efficient. The next, so this is a working example to just try to explicit the idea. These are 2 sentences that are from the Penn tree bank with their semantic and syntactic trees. And let me just highlight all the path of chain dependencies of length 1 that they have in common that you have here in red. And you also have the intersection and the union I'm keeping track of. You could do the same for 2. And if you just combine the 2 then, and then take the intersection over the union, you'd get some sort of similarity score of 0.75. So the idea is that whatever maximal value of k hat we choose allows us to tune how deep into the chain of dependency we're looking when we're considering the structural similarity between 2 graphs. Okay, let's just jump into results for that first experiment. And this is using data from Simival 2015 shared task 18, which was a task on syntactic and semantic parsing. And the idea is that we are going to have syntactic trees as well as different semantic graphs for multiple sentences. And we're comparing 2 ways of assessing distributional similarity. One is paired score, the other is a word mover distance, both of which are fairly common in the NLP literature. And we're testing different values of k hat between 1 and 5. And really, there's 2 things you can point out. The first one is that the highest correlation score that we get is always with syntax rather than with semantics. And in the case of paired score, there's like a very large gap between the 2. The second point that's also very interesting is that when we go to higher values of k hat, that is when we look at longer and longer chain dependencies, we get worse scores. So it's more like we consider whatever we capture with distributional representation seems to be more aligned with shallow structure rather than deep chain dependencies. And we can also point out that PSD, which is the one that has an uptrend on WMD, that can perhaps be explained by the fact that it's known to be somewhat different from other formalism or semantic annotations, but that's not something we look into every day. Okay, so to recap that first experience, we were interested as to whether we had some evidence that distributional representation would align with semantic structure one way or another. And what we see is that if you just take off-the-shelf available tools, you tend to have something that allows more, that aligns better with shallow syntactic structure rather than semantic structure. Okay, moving on to our second research question, which was about whether representations actually capture something as semantic features. And this is something that we can break down into 2 different sub-questions. The first one being, can you convert a dense embedding into a old style like binary vector that we could then possibly interpret? And that second question is, if we do manage to do that empirically and practically, then can we interpret the Booleans in a way that makes sense? And would these Booleans actually encode something that we would want to call semantic? Okay, so starting with that first sub-question, the simple thing that we do is that we have a simple NLP autoencoder. And the idea is that we are going to have a encoder that is going to map a dense embedding onto a representation bounded where all the components are bounded between 0 and 1. And we have a decoder that then takes that latent representation and that just tries to recreate whatever the input was. And in order to ensure that the encoder produces binary representation, we have a bunch of tricks. The two more important would be that we have a curriculum. We just basically round components more and more as training goes. And we also have a auxiliary loss. This one is a lot more important. The idea being that whatever the output components of the encoder are, they should be as far away as possible from 0.5. And given that they're in a 0 or 1 interval, this strongly encourages the model to go towards binary representation. Okay, during testing, we just simply binarize everything to by rounding so that we get actual bits instead of these float values. Okay, so having a look at whether this setup actually works now, what we do is we just run a simple hyperparameter search using Bayesian optimization to have a principled way of looking at all the possibility of training that kind of thing. We're looking at English word-to-vec embeddings with 300 dimensions, and we're testing latent Boolean dimensions of 5,000 and 10,000. So these two, we have one separate search process for this. And having a look at the results. So here's a histogram of all the MSC scores that we get for all the different models that we see in our two searches. So the idea, for instance, is that if you look at if you look at this bar here, you would see that the majority of these these embeddings where the latent dimension is 5,000 fall into a bin that is somewhere between 0.12 and 0.14, if I remember correctly. There's also two baselines on that plot. The black one is what happens when you just use as a reconstruction the average of all vectors in your training set. And the red one would be what happens if you compare a vector to its nearest neighbor in terms of MSE. So the general idea is that you want to do better than these two baselines. And as we can see, it's really a matter of trade-off because you want to have enough components to actually get something expressive, but you also do not want to have too many components as this can lead to a failure of actually training these models. So there are practical and empirical challenges as to how you can do that properly, as to how you can transfer distributional dense vectors into Boolean vectors. Okay, so we now just look at whatever these models fare the best in terms of produce the most accurate recomposition and reconstruction, and we're just going to have a look at what its complement actually encodes so as to tackle our second sub-question. And what we do, pretty simply speaking, is that we just have decision tree-based classifier for binary tagging. And again, we set the hyperparameters using Bayesian optimization so that it's principled and we don't really have to deal with it. So the idea is that we're going to learn one classifier per tag, and we're just going to work on a balanced set of tags. We'll have two different type of tags. The first one would be supersenses that you get from LearnNet. So for instance, if you have the word presenter, then you would say that its supersense is person, and likewise for Frenchman, it's also person. And the second type of tags that we're considering are part-of-speech tags, so adjective, nouns, adverbs, and verbs, as you have listed on WordNet. And right, so we're just going to also compare results that we have both with Boolean vectors as well as with the original dense embeddings before the binarization process, just to make it, just so that we have like some point of comparison. And right, so this is a general view of how accurate the different classifiers are. We have 5 different classifiers for every tag. You have 4 different groups on the left side of the slide here. You have everything that relies on supersense tagging. On the right side, you have everything that relies to part-of-speech tagging. And then you have Boolean followed by the original dense vectors for each of these. So to take a concrete example, if I look at my artifact supersense with that orange column here, that would be that on average, the dense embeddings achieve an accuracy of 0.7 at using a decision classifier at just predicting whether a word is an artifact or not. And right, so there's really two things we can point out. The first one is that in general, when we look at syntactic tags, we get classifier trees that are more accurate. And the other thing is that very interestingly, the Boolean vectors also get classifiers that are accurate. So that's something you can see by comparing the average tallness and looking at the supersenses, which is going to be lower than when looking at the POS tags. And for Boolean vectors, just notice that the column that corresponds to Boolean vector always systematically is higher than the original results for almost systematically is higher than for the corresponding semantics. But accuracy is one thing. We might also want to have a look at how straightforward it was to derive these classifier trees, and so we might want to have a look at the structure. And there we would have, this is for instance as a proxy, we can have a look at the number of leaves that we have in our best classifier for all of these tags. And same plot as before, you have your supersenses on the left, you have your POS tags on the right. And really generally the same observation would hold, is that you would see that syntactic tags tend to yield classifier that have fewer leaves, and Boolean vectors as well tend to produce classifier that have fewer leaves. There are some cases that are obviously less well-behaved than the others, like for instance, the verbs are pretty obviously out of line in terms of the rest of the part of speech. This isn't really something we could gotten to yet. That's an interesting result. And this is something that I point out with respect to number of leaves, but obviously we could also verify the same thing for depth and have virtually the same things. Okay, so let me wrap up this second set of experiments. We were interested as to whether there was some evidence that distributional representation do capture semantic features. And what we saw is that if we just take static word-to-vec embeddings, then in general, we get better results when trying to predict syntax out of them than when trying to predict semantics out of them. And very interestingly, we also see that binarizing word-to-vec embeddings do give us things that are more readily interpretable, and that tend to produce more accurate decision tree classifiers with simpler decision trees. So again, not very clear cut. Okay, well, then just let me conclude the whole talk now. So that was where we started. We were interested as to whether if we construe distributional models as something that model the probability of a word given a context, you still need to believe that they also encode something semantic. And really what we saw today was that first, when we look at distributional similarity metrics, they tend to align more with syntactic structural information and shallow one at that, rather than semantic structural information. The second one, we saw that empirically, it's not straightforward to actually convert a dense embedding into a Boolean vector. So there's a format difference that is hard to overcome. We also saw that both when we took our binarized Boolean vectors as well as the dense embeddings, that we tended to align better with syntactic tags rather than semantic supersense tags. But however, we did see that going through these panes actually do yield more explainable and more understandable representations than what we had. And in terms of where to look next, obviously we haven't really talked a lot about contextual embeddings here. That's kind of an interesting next step, especially given that Scala is known to possibly have interesting consequences on the sort of things that are captured in embeddings. Another point that would be very interesting to look into is that semantics isn't just about structure and features. There's obviously, and especially for use-based models of semantics like distributional semantics, it makes a lot of sense to have a look at symbol grounding, but as well as interaction between speakers and see if these things are captured one way or another into the distributional representation. Yeah. And here I tried to push back against the idea that this is distributional semantics, but maybe it would be also interesting in terms of completeness to see whether distributional representation do always systematically encode some part of semantics, even if it's less than what we see for syntax. Okay, I think that's all I have in terms of slides, so I'm happy to take questions if there are any.
So we have 2 minutes for questions.
So thank you very much for your interesting talk. So just a clarification. So regarding the first experiment, can structure similarity be applied to syntax other than dependencies and so such as DCD? So do you also do that kind of analysis?
This isn't really something we've discussed yet with Timothee. I think the only requirements that we have for that metric is that whatever representation semantic you have would be convertible into a directed labeled graph. So I assume that you could do that. You would probably need to work out like the exact algorithm to convert one into the other before you do that, but it should be possible.
Thank you for the talk, and the results are very interesting. And I'm wondering, what is your motivation for comparing Boolean representations with dense representations?
On a very practical point of view, to know if my pilot code is actually working, that's like a start. If I manage to have some sort of Boolean representation, but I actually get results that are very much worse than what I get with whatever input, then it's reason to doubt myself. That was the original one, but I think Timothee has also a better reason there.
Yeah, I don't know if that's the question. Maybe you're wondering why we're doing that, why we try to convert the dense vectors. Yeah. So the intuition was the thing is the dense vectors are usually not considered to be interpretable. You know, they encode a lot of information, but we don't really know what and really how in an intuitive sense. And the idea was to try to force the system to produce interpretable, vectors with binary, like old school features. Maybe some features indicate syntactic features or semantic features. And so really the idea was to try to see whether that's possible, to try the system to tell us what is encoded into vectors.
Right, to elaborate very quickly on that, one of the preliminary experiments that we did pretty quickly was to see if we could identify like specific booleans to which we could assign specific values, or combinations of booleans to which we could assign specific values. So,
okay, Ashley?
Thanks very much for your talk. I was wondering how fine-grained you were when you were considering syntactic information like part of speech tags. Were you basically bagging everything together, or were you looking at particular instances? Because some parts of speech will be harder to identify than others, and more indicating of structural aspects.
So in terms of, we mostly rely on word nets, and so that's the granularity we have. We have the core part of speech that you have in word nets, so adjective and verb, noun and verbs.
But none of these are functional elements.
No, I don't think so.
But the functional elements are key to
Yeah.
indicating structure.
Yes, and we didn't really look at that in the specifically for experiment 2 with the tagging experiments, right?
Yeah.
We didn't specifically look into that. There's a couple reasons as to why that is a bit unhelpful when it comes to distributional semantics. We know that the frequency of a word strongly impacts how central it is to the rest of the distribution, and so very often, like functional words tend to be vividly different from the rest, simply by virtue of their frequency. And
Because they're high frequent, or
because they're very frequent. They're very frequent, yes. And they're known in the literature to have like very different profile from the rest.
yeah, no, you'd expect that because they're really different
And so
But they're more indicating of grammatical relationships and structure.
yes.
And that seems to be what you were trying to find out about.
I think here we were
the more lexical words.
Yeah, we were
less
more
interested.
interested about the lexical components that we would get into individual word. These are static embeddings, so the idea that they should represent word type, and we were interested as to whether the lexical part of that aligns more, again, with syntactic information rather than semantic information. So in terms of structure, we have that first experiment, which was specifically designed to have a look at whether structure, semantic or syntactic structure was more in line with what we see.
Okay, so I'm also wondering about the, I mean, you basically linearize everything in your counting the distance, but that's kind of losing a lot of information about, you know, what your intervening nodes are and what their functional contribution is to the structure.
No, these are sequences of labels. So
The sequences of labels.
right. So an example here would be, for instance, one of the edges of label 2 that you have is that in these two sentences you have a n subject has an n, and they're sequences, they're ordered. There's really a lot of information.
And so if you change the constituent trees, then you'd have like MP subject.
Yes, you would
IP
have that.
matrix.
Yeah, you would have that.
Do you think you get different results if you push the constituency?
I still think that
Yeah, that's
I still think like the core results will hold, that we still see more, or that distributional representation would still be more in syntax. That's something I'm willing to bet a year on. So if I ever do the experiment, catch me up and I'll tell you.
Okay, thanks.
Okay, we have 3 minutes or more. Do you have any questions? Yes.
That's a clarification. So in this metric, you just take into account relations, but ignore labels on the nodes, right?
Yes.
Okay.
We did experiments also with sequences of nodes and sequences of node plus sequences of labels, mostly the convolutional. So it's a bit difficult then to see exactly how you would, like there's different possibilities to how you would implement that precisely. And so we went with the reporting the one thing that seemed simple and more intuitive. So to ignore whatever lexical components themselves was and just look at the structure itself.
Okay. Any questions? May I ask one question? So I'm always wondering about the phrasal similarity between the two phrases which have quite different structures. Like the one is just one common noun dog, and the other is like complex common noun like the mammal that typically has a long snout and likes to bark. Yeah, and those things, really has a very acute sense of smell. But the same notion that they are quite different structures. And maybe the context itself might be different.
So that's a bit beyond what we have in the paper, but I have a lot to say about that. My PhD was specifically about whether distributional semantics and lexicography definitions are equivalent. And the short answer is no, they're not. They tend to have very different profiles. You tend to not have very high correlation when you're trying stuff like RSA. You tend to struggle a lot when you try to have a neural network generate these kind of things, unless you rely on patterns, basically. So just like defining parenthood as the state of being a parent, which is interesting, but maybe not as fine-grained as what one would hope, and not as semantically driven as what one would hope. So the short of it is that in general, the vectors that we get for a single word and whatever representation of a full noun phrase trying to describe it tends to be different in my experience.
So we need something more years, except words.
Yeah, I don't think distributional representation capture compositionality very well in their current state, by the way. There's some things that are compositional, but some others that are a bit more difficult to get.
Thank you very much. Next, speaker.